Welcome to this lecture where we will go through the steps of mounting a solid oxide cell in a rig. We are from DTU Energy, and today we have two researchers who will go through all these steps with us. We have Anke Hagen and Vasilis Pilalis. Before we get started, I would like our presenters to say what their experience with cell testing is.
Yes, I work with the development of solid oxide fuel and electrolysis cells. I have done that for many years, and that involves testing electrochemical characterization of performance and durability, state of health, and that involves a lot of cell testing, and that's my experience in mounting a cell in a rig.
Regarding myself, I'm currently working as a postdoc researcher in DTU Energy. During my time in DTU, I have mounted, assembled, and tested many different cells. I have experience on impedance spectroscopy, on impedance analysis, and I use the skills to study and understand better the performance and the durability of solid oxide cells.
Mm-hmm. So, two very good researchers. Enjoy the lecture.
As you can see in the video, here we are in the sample preparation lab. This lab is equipped with all the necessary tools and materials required for mounting the cell into on the test house and then put it on the test rig.
And now you start seeing all the components we are using. You see this kind of white test house, and that is made of alumina. Did you know that we actually sold these test houses to partners, to commercial partners?
Oh, recently or like?
Yeah, actually, it started with that when we started the solid oxide fuel cell research at that time at the Risio National Lab, we needed a test house, and you cannot purchase them. There are a lot of challenges when you want to test a solid oxide cell. You need the high temperatures. Yes. You need a lot of probes to understand the performance. So first is choice of material. So we chose aluminum oxide because it has a suitable thermal expansion coefficient, and it is quite inert because we have to go up in previous times up to 1,000 degrees centigrade. So that was the materials choice, and also the design of how we are allowing the gases to flow over the cell. That is actually quite a lot of knowledge that we developed. We made a path inside this block where the gases are passing and entering into the cell compartment and exiting. We also designed what probes we would introduce, what we would measure in temperature, voltage, and current, etc. And that was actually a know-how that was valued by some partners, and we sold them commercially.
Oh, I didn't know that.
Yeah, no longer, but that was actually a know-how we developed, and that is a very valuable know-how, and we have, since the beginning, had many versions of better and better cell houses to make good and reproducible testing and detailed electrochemical
characterization. Okay, very interesting.
Yeah.
And I guess this is the inlet that you mentioned.
Yes.
So this is where the fuel gas is entering into the cell compartment, and this is where we also have the outlet. And as you can see in this video, in this image, that the user tries to clean the probes, the electrical probes, which are used for applying the voltage, but also for measuring the voltage. So it's quite important from time to time to conduct this kind of cleaning in order to remove any residuals that can increase the total resistance of the measurement.
Yeah, here you see 4 probes that are actually the wires that come from the bottom and then will be contacting the cell or the contact layers on top of it.
And now we enter the bit more complicated step of the process. So as you can see here, the user tries to measure the depth of the recess. So the probes that Anke mentioned are not in the same plane of the alumina, the surface of the alumina plate. So for this reason, we have to measure how thick this recess is in order to fit the thicknesses of the following layers. Here you can see the different compartments that are necessary for properly mount the cell. So you can see the gold sealing and the two nickel meshes. So these layers should have a thickness that fit the recess, the thickness of the recess, so that we can have a good electrical contact and also minimize the possibility to have a gas leak.
So here we are adjusting the thickness of one of the layers. And that's another way to adjust a thickness by a very, let's say you can adjust through a very specific thickness. So now this is to get the contact to the wires. You see here the 4 wires that stick up. And you have to make sure that the contact is there's a good electrical contact to the plate you are putting on top of it. And for that we are using the platinum paste.
Yes, as you can see in the video, some glue is used in order to further stabilize the whole structure. We use an in-house synthesized glue, which is is organic based. We do that because the commercial glues, we found out that they have some silica impurities, which silica is a kind of degradation factor that affects the performance of the cell.
So now this is the first contact plate, nickel, and actually you can reuse all this often from one test to another. You don't need to have this step repeated each time you start a test, but after a few tests this contact plate needs to be replaced, and that is what you saw here in the video.
Anke, did you use glue in the past?
Actually, we did not, but in the setup we are using now, we have a lot of layers, and that they can slide when you are doing the mounting and the transport. And that's why we are fixing those layers by glue, and that glue will evaporate. So it will disappear when you are then actually doing the actual test. And one more thing, actually, you see here a gold frame. And that is also a more new development. Originally, we used glass ceramic seals, and they are very good to really give a gas-tight compartment. And they were used for studying solid oxide fuel cells for many years without any problems. And then we discovered when we go to solid oxide electrolysis, then actually we are starting to leach out in high steam content, in particular the silica or silicium to silica that is in this glass ceramic seal, and we started to actually poison the electrolysis cell, so we would interfere with the inherent cell behavior over long term, and that's why we went over to the gold seals.
Okay.
I don't know how difficult this handling is, and it seems also very expensive to use them, right?
Yeah, it is expensive, I guess. But as you mentioned, it improves the performance of the cell a lot. And we can also reuse the gold sealings unless they are cutted or they have been exposed to very high temperatures, and we can see some very visible degradation of the sealing. But otherwise, this is a good thing that we can reuse these expensive sealings for quite many experiments.
Yeah, and that we could not with the glass sealing. It was also the demounting was very elaborate. So in a way, it is also easier to mount and demount the cells with this gold sealing. Yeah, now we have different meshes, as you see, and these meshes are to allow the gas distribution over the cell. And we use fine and finer and coarser meshes for allowing gas to flow and don't hinder the gas to reach all parts of the cell. Now, wow, this looks quite interesting, yes. This cell, right, with the black stripes here, right?
Yes. It's not the ones that I used to mount.
Yeah, so normally you would have one big black area, which is the oxygen electrode. Here, this is a very specific test we are setting up. It's called a segmented cell, so we can follow how the performance and also the durability is progressing along the cell, let's say, area. Normally, you would have just one black square for this electrode. And this is actually now the air electrode side. The top here, you see a hole. So later on, there will be a block placed on top of it that will touch the oxygen electrode side.
And you can see that we use tape in order to stabilize the structure and facilitate the transfer of the test house to the test rig. And as we mentioned before, we use glue to avoid the drifting of the different layers. For a similar reason, we have used also the tape.
And here we have to focus on the top part that allows us the fuel mixture or gas mixtures to the fuel electrode. And you see there are different inlet opportunities, so we can give hydrogen and steam, carbon monoxide, dioxide, depending on what kind of test we want to carry out. We can mix all this or lead all these gases on top of the test house, and then it will go into the gas entrance tube.
Yes, you can see here that the test house is placed on two wooden blocks. This is not a coincidence. We place the test house like in that way so that we can avoid adding extra unnecessary stress on the wires that, as Anke mentioned, they are coming from the bottom of the test house. And in that way, we protect the wires from unnecessary degradation during the transfer of the test house.
Yeah, and now we are in the electrochemical test lab, and we are quite proud of having such a facility, which is, I think, quite unique in the world. We have here on this side expanding in all directions test rigs for single cell testing, more than 20. And on this side, we have stack testing facilities, both for short stacks, where you only have a few stacks, cells like 10 or 20. And then also we are capable of testing full-size stacks, commercial stacks. We can accommodate all sizes, geometries of all the major players. And all this test lab is equipped with central gas lines that give a safe, let's say, opportunity to use many gases for testing for diagnostics. That includes explosive and toxic gases, hydrogen, carbon monoxide, oxygen, nitrogen, etc., methane. And then we have a very high degree of safety in each of the test rigs that you will be seeing later. And all the rigs and all the tests can be controlled by software that we have developed in-house and can also be controlled remotely, so we can carry out long-term durability testing over months and even years. So this is a short glimpse of one of the homemade test rigs that we have, where you will have the furnace, where the test house comes in, and then you have around it a lot of valves and mass flow controllers that control the gas flows that go into the cell. And in addition, we have a lot of sensors placed everywhere that measure the concentration of explosive or toxic gases, like we have CO sensors, we have hydrogen sensors, measuring that the ventilation is working. And if anything goes wrong, then we have a safety procedure that gradually shuts down the test and puts it into safe conditions, both safe for the cell, but also safe for the environment and for the people.
Yes. Here you can see the different electrical wires. As you can see, the gold ones and the thinner ones, which are platinum wires, and they are used for the voltage measurement, while the current, the gold wires are used for the energy input to run the cell, and they are connected in a different places in the test rig. So here we can connect the voltage wires, and you can see we have different ones, so we can measure the different segmented parts, as Anke mentioned before. But also when we have a big cell, we can measure the in-plane voltage, which is also quite important, that as an extra indicator of the performance and the degradation occurring in the cell during testing. Here you can also see the user tries to align vertically the inlet, the air inlet. This is quite important, because if the inlet tube is not aligned properly, then maybe a cavity is formed, a gap is formed between the inlets and the oxygen side of the fuel cell, of the cell, and this could increase the possibility to have a gas leak that will decrease the nurse potential of the measurement.
Seems very elaborate, right, to adjust by manually, right?
Although sometimes it's important to leave some space to the tube to follow the softening of the cell, because the cell, when it develops a high temperature, it becomes a bit smaller. So it's important that the tube is allowed to follow this shrinking.
Shrinkage, yeah. Yeah, one has to keep in mind, right, when we mount at this room temperature, then you heat up, and there are a lot of expansion or shrinkage, settling of layers going on, so you need a bit degree of freedom for movement of these tubes that are allowing the gas to come in. Oh yeah, and now here we see actually there's a block here with a few golden wires, and that is actually the block we are putting into this, let's say, into the top block, and that is covered by gold for electrical contacting. So the mounting we did not see here, but that is of course an important part. And on top of that block, we have this vertical tube that Vasilis described will admit the air, and that has to be aligned.
Here you can see again more from closer perspective the inlet, the voltage wires where we connect them. So you can see we have at least 4 in this case, 2 for the anode, 2 for the cathode.
Okay, so you might wonder, there are a lot of other wires you see, like the red and the blue one, and then you see also some tube going in here, because what you saw before is more or less the cell we have mounted. However, in order to characterize the state of the cell, we also want to know about the temperature. So we have a number of thermocouples. We have a few that are placed in the center of the cell, the inlet, the outlet, and also different places prior to that. And in addition, we are using a concept with PO2 monitors, and they are placed inside the fuel channel and also in the outlet. And what are these? These are actually electrochemical sensors that measure the partial oxygen pressure, which is more or less, you can relate directly on the steam to hydrogen content in the fuel by the Nernst potential. So you have always a measure what gas you are sending in to the cell and what gas comes out. So you can measure directly things like gas utilization. And in particular, when there is something going on the cell, it is nice to have many probes and many parameters you measure, because then you can trace what kind of phenomena you see and maybe explain and relate that to a gas composition related to a temperature, to a potential leak and things like that.
And here you can see we add some extra weight on top of the air tube. And we do that in order to facilitate the following of the tube during the softening of the cell when we are we're in high temperature, and also to improve the electrical contact as much as possible. Here you can see that the user is adding some thermal insulation, and this is very important in order to have a control environment so that we can be as certain as possible that the temperature that the cell operates is the one that it's homogeneous, and that the performance can be can be correlated to the operating temperature.
And also, like, imagine it's a really big space where the heat can evolve, and you don't want to have everything getting hot in the test rig. Yes, that's very manual, right?
Yes.
We have typically everything is controlled by automatic valves and mass flow controllers, but there are a few things that we still adjust manually.
Yeah, this usually we do it during the beginning of the test, and then the whole control becomes automated.
And I think that it's also on purpose that this is manual, because that are the gases, if there is a power failure, then most of the gases, of course, will be shut off. However, these are the kind of safety gases that are not explosive and not toxic, and they rely on a manual valve that would not be affected by any power failure. And here you see a selection of the gases that we can apply, some of them for realistic reasons, others for diagnostic reasons, to understand and learn how the cell is behaving when you're applying different kind of gases. Yeah, now we close the door and start the measurement, and hopefully everything was fine. That we will actually see when we run a test protocol where we are measuring voltages, open circuit voltages. We are varying the flows where we can discover if we have a good contact, if the setup is gas tight as desired, and then where we can start the actual measurement. So
Yeah.
you always hope that everything went well.
Most of the times, and quite many times the things do not go as planned, but when they go, then we can start conducting impedance measurement under different conditions, as Anke mentioned before, in order to understand better the mechanism occurring during the testing of the specific cell. Cell testing is not always successful. It's quite challenging, but this should not discourage us to try again, try more, fail better. And I hope this video and the explanations will be useful to future users that are interested in hydrogen technologies.
Yes, thank you, Vasil. I can only join you in it is quite a challenging job, and we have many years of development and gone through different iterations of making it better and better. And yeah, I hope you enjoyed the video, and thank you for listening and watching. What I find challenging in all this mounting process, there are so many manual steps, and I think in particular this assembling of all the layers is quite time consuming and elaborate, because you have to, you saw there was a lot of measuring thicknesses and so on, so you need to have the right height of all the layers that later on you can compress everything so it's getting gas tight. And on the other hand, you also need all the layers to get in good electrical contact with each other. And there, I think many of the misalignments or mismatches can happen that then later on lead to a not successful test that you then immediately measure in the open circuit voltage or in other of the parameters you are measuring.
Yes, I think I would agree with Anke regarding the formation and the shaping of the different layers, especially the corrugation part. Many times I remember trying again and again to reach the suitable thickness, and this is time consuming, and that you have to be patient, because if something doesn't go well, then you have to repeat again the experiment. It depends on the user, I have to say, but based on my experience, I wanted to be very careful. So it will take me like maybe even 4 hours from assembling the cell to finalizing the mounting on the test rig.
Yeah, and maybe one of the experiences is never rush. So starting to mount on a Friday afternoon is a very bad idea. Often we are under big pressure with projects we have to deliver. However, in particular here in the mounting, many things can go wrong if you are in a rush. So always make a good planning and take you the needed time to make it. Yeah, I think maybe you also learned it from somebody experienced. So we typically introduce new people by that they are following another student or researcher to mount a cell. In particular, there are so many manual things and sometimes easy fits or tricks that are good to learn and to observe. So if you have to do it, then we need to follow, or you need to follow a person observing it and then trying with another person watching it and being a kind of supervisor to make sure that everything is aligned. But it is actually a manual work, so one should not be afraid of doing it. It's not. It just requires concentration, so to say. Yeah.
Yes, I would agree with Anke. Always ask, don't hesitate to ask a more experienced researcher, because there are tricks that are not written in books, and many researchers have spent hundreds of hours in the lab, so that the next generation of researchers could work more efficiently and faster, and also safer in the lab.
And may I ask you what went mostly wrong? So you have mounted a test and started, and something is wrong. So what are the most probable failures that during the mounting process?
So I would say that maybe the alignment of the oxygen tube could be something that we should double check sometimes, and also again how tight is the tube, and this could be reflected either in a unexpected value of OCV, so this indicates that we have a kind of gas leak, or in a very high ohmic resistance. That is another indication that the electrical contact is not optimized, so we should maybe add some extra weight or maybe reduce some kind of or reshape some of the current collectors in our next effort.
It's the same experience. So there's this match of all the layers giving both a good sealing and then at the same time also giving good contact. That is probably the most serious challenge here. And in my experience, it's very difficult once you have mounted and started and heated up to do any fix to the setup. In fact, you don't often succeed. As you mentioned, you can apply more weight to compress, getting a better contact. There are no limits to that. So actually, the best advice is make it right from the beginning, because fixing it once it has been hot is quite a difficult undertaking, right?
So Anke, I was wondering how many things have changed through the years, starting from Riso, now being in Lyngby.
That's really quite a lot that has changed. I mean, we still have this block, and that's more or less it, and also the basic design, but we have changed the sealing concept, we have changed the contacting, the gas distribution layers, coming from ceramic now to metallic plates. So there have been many evolvements of the design of this test house and also how we do the testing. However, there's one thing that we are in particular proud of, is that when we then actually start the test, we have a standard protocol, and that started way back in the beginning of 2000, where we are measuring at similar conditions, and we are actually also proud of our data collection and documentation, so we can still go back to the very first tests we have done, find the data on a central data storage system, and can compare to what we are doing now. So that is actually a huge source of knowledge and of data that we have, and that is difficult to find in the world. So the colleagues that have designed the testing and started it have been very foreseeing in how to collect the data and store them, and that is in fact a huge source of knowledge that we should harvest more. Yes. So what is the longest test you have run?
I think it was around 5,000 hours.
5,000 hours.
5,000 hours, which is quite challenging,
considering
potential like power shutdowns and.
Were there any interruptions happening?
I think only once, but we were lucky enough that the cell survived. Based on my experience, many times when there is a power output or there's something, a pump doesn't work or a valve doesn't work properly, then the cell might experience some fatal degradation.
Yeah.
So 5,000, but most of the times it was around 1,000 hours. Just
so quite some time.
Yes.
Yeah.
It's quite. What about stack testing? I have never done. I think we have also equipment for stacks, right?
Yeah. Now you see, I mean, all this stacking of layers will be different, of course. No? Typically, we get a stack from a commercial supplier or our own development. So then you actually have the stack, and there's quite a different process of mounting a stack, and it is also depending on the stacking design, how you connect the gases and how much you employ a weight or whatever sealing concept the stack is using. So there are not as many manual steps involved as it is here for cell testing, clearly. Yeah.
So the whole mounting thing is the mounting procedure. Would you consider it maybe a bit simpler compared to a single cell testing?
I would say unless you are having, if you have a stack with 10 cells and you contact each of the cell, then you have, of course, the connecting the wires is a lot more elaborate. However, all this gluing and stacking extra layers that is already kind of hidden in the
Yes.
stack.
Yes,
But
right.
for stack testing, the contacting of cells or cell groups, if it's a bigger stack, that is probably also quite time consuming.
Okay. And I know that you have also involved with experiments with CO2 electrolysis, right, or syngas, while I have mainly focused with steam electrolysis. Is it like, I was wondering what is the longest experiment that you have been involved with?
Yeah, for this co-electrolysis that involves steam and CO2, also several thousand hours.
Several thousand.
Yes,
Okay.
yes.
Okay.
So the duration is probably similar as for steam electrolysis, yes.
Okay.